Okay, having defined the concept of resistor and resistance, we can now look at some examples how we might calculate the value of a resistance of a certain resistor. It is easy to calculate the resistance if the cross-sectional area is uniform and if the resistivity of the material is also uniform. It's just, it's just a rho times L over A, right? But what if I have something like this? Okay, it's a uniform material with a uniform resistivity rho, but it's cut into a shape like this. It's like a cone with the head chopped off. Okay, so the cross-sectional area increases linearly between this point and that point. The total length is L. Okay, and if we try to establish a current flow between this surface and that surface by establishing a potential difference between the top surface and bottom surface so that the current flows this way. Okay, can you tell me the resistance R of this strange looking resistor? Right? How do we figure out this problem? Well, we know the current flows this way, and as the current flows, it encounters bigger and bigger cross section, right? So for the same lengths, for the same rho, you find that the resistance drops as it goes forward and the current flows forward, and therefore it is a non-uniform situation. We have to be more careful about it. Now, the current has to flow through a succession of layers. Let's look at this particular layer. Okay, let's look at this particular layer. This particular layer has a thickness dx. X is, this is the x-axis, so it's got a thickness dx. It's got a certain radius, which we can easily figure out later. So we can figure out the resistance of this particular layer. All right, this particular layer, and let's call it dr. Let's call it dr. Now this dr, if we apply Ohm's law to this little piece dr, then it says that the voltage difference across the two ends of this layer, which is dV, must equal to the resistance of this layer dr times what? Times the current. Now be careful here. The current is the same throughout every one of these layers. Okay, the current flowing through here and the current flowing through there are exactly equal to each other. So I is really the same for every layer. Why is that? Because otherwise, look at what happens. Suppose you got more current flowing in and less current flowing out. Okay, then as a result, this whole piece, due to the conservation of charge, you get more going in, less going out. There will be an accumulation of charge, right? It gets, it's going to build up a positive charge, and we know that doesn't happen in a real circuit. Charges can only flow from place to place. They do not get accumulated or depleted, and therefore every one of these layers have the same exact current. Okay, the same exact current. They don't have the same R value, but they have the same current value. Now, if I then integrate, okay, between here and there, adding the contribution to every layer up, the integral over dV, just add all these little dVs up, what do I get? I get a total voltage difference. Right hand side equals to I is a constant, which I'm going to take out, integral of dr. See, that would be a generalized version of V equals IR. That's how we calculate the resistance R. Okay, so R really is the integral over dr. Again, what is dr? dr is the electrical resistance of this little piece, this little disk from here to there. Do we know how to calculate dr? Yes, we do, because since dx is very small, the cross-sectional area over dr, over this little piece, this R, whatever that is pretty much a constant. Okay, pretty much a constant. And let's see what is that equal to. All right, let's see what is that equal to. See, this is A. All right, so let me draw a simplified picture here so we can see it more clearly. This is A, right? This is A, and this angle is theta. This is R. That's what we're looking for. This distance is X. Now, what is R equal to? R equals this value plus that value, right? This value is just A. What about that value? Look at this. There's right angle triangle here. I'm looking for this, right? We know what that is. That is X, and this angle is theta. So isn't that equal to X times tangent theta? Right? Okay, so the total value of R between here and there, R, is equal to A plus X tangent theta. Okay? Tangent theta. So there we go. Theta is a constant, okay, no matter how far you go. because it's a straight line. So given r, what is the cross-section area of this little piece? A would be equal to pi r squared. Okay, pi r squared, and that is a pi times a plus x tangent theta squared. Okay, given the cross-section area, what is dr then? Dr, by definition, rho times the length or the thickness dx divided by what? By the cross-section area A. Okay, so that's dr, and let me copy that. Let me copy A here. It's rho dx over pi a plus x tangent theta squared. That's dr. Okay, given dr, all I have to do is to integrate, then I get r. So what's r equal to? R equals to integration of dr. And then that's the integral I have to do. Take the constants out, rho over pi. Integration over dx, going from here to there, going from 0 to L, right? dx. A plus x tangent theta squared. That is all we have to do. Okay, now at this point, I'm going to leave this as an exercise for you to finish this integral. I mean, it's quite simple to do. A is just a constant, so you can redefine a new constant, a plus x tangent theta, to substitute for x, and then just like, let's call that new variable u. So it's just basically du over u squared. Okay, you can easily work this out. And tangent theta can also be figured out if you know what that distance, if that radius is b, then tangent theta will be just b minus a divided by l. Okay, so this tells us once we're given a dimension a, b, and l, and the resistivity of the material, we can find r. Okay, and in particular, if a and b are equal to each other, you should recover the same result, which is rho times pi a squared. I'm sorry, rho times L divided by pi a squared or pi b squared. They're the same. Okay, so this is an example of an uneven cross-sectional area. Now let's take a look at our second example. This is a very common setup. It's called coax cable. What we have here is basically a conducting material. Okay, it's cylindrical, but it's got a hole. It's got a cylindrical cavity inside. So it's got inner radius A. Between here and there is vacuum. There's nothing. And then outer radius B. And between A and B, there is a layer of uniform conducting material of resistivity rho. And the length is L. Let's say L is pretty long, so that we don't have to worry about, if you look at a typical point, it's inside this material, it's quite far from either edge because L is very long, so we don't have to worry about edge effect. Okay, what is the resistance R of this coax cable? Well, this question cannot be answered unless you tell me how you wish the current to flow. Do you wish the current to flow along the cylindrical axis, or do you wish it to flow from the inner surface to the outer surface? That is very different. Okay, to do the first, you need to hook up a battery between this face and that face. Okay, between this, circular region and that circular region. So you connect it like this. Okay, but to let the current flow from this surface to that surface, then you need to hook up the inner cylindrical surface to a certain voltage and the outer cylindrical surface to another voltage. In other words, you connect the battery like this and like that. Okay, you will create very different current flows, and therefore the resistance will also be very different. Now in the first case, if you wish the current to flow this way, okay, that is a piece of cake, because as the current flows, does anything happen? Does anything change about the cross-section area along which the current flows? No, not really. It's basically this big area minus this small area, right? That is the area available for the current to flow. So I would simply have a uniform cross-section, and R would be equal to rho times L is the length along which the current flows, divided by the cross-section area, which is pi a squared minus b squared. I'm sorry, b squared minus a squared. That's it. So that's trivial. Okay. Of course, we're not going to stop here. We're going to look at a more interesting case where the current flows radially outwards from this surface to that surface. Okay. Now to do so, let us draw our cross-sectional area, cross-sectional view. Okay. cross-sectional view. So this time I'm going to hook this up to a positive terminal and hook that up to a negative terminal. Here's the cross-sectional view. So the current will now flow radially like this, okay? Actually from here to there, radially. You still have cylindrical symmetry, but the electric field between here and there is no longer uniform, okay? It is no longer uniform. Actually, you can probably remember it from the previous discussion on cylindrical symmetry. The electric field should go like 1 over r, okay? 1 over r. But we can see exactly how we calculate the resistance. Again, just like the previous example, we can imagine as the current flows from here to there, it has to encounter different layers, okay, different layers of the material, and each layer is in the shape of a cylindrical shell, right? So here's a cylindrical shell like this. It's like this. Okay, and this cylindrical shell has a radius between r and r plus dr. So the thickness of the shell is dr. So the current has to flow from this layer to that layer, clearing this shell, and it has to go to the next shell, next shell, and next shell, and so on. Okay, you can easily figure out the resistance of each shell, which is dr. Okay, and then just like the previous case, if you integrate over dr, you will get the resistance between here and there. Okay, so what is dr equal to? Dr depends on the resistivity, rho. It depends on the length of this layer from here to there. That's the direction along which the current flows, and that's just dr. It also depends on the cross-sectional area of this layer. What's the cross-sectional area? Well, it will be the circumference multiplied by what? By the length, right? By the length L. So that is the dimension L. Okay, that's the dimension L going into the paper. So that will be 2 pi r times L. All right, 2 pi r is circumference times L going into the paper. It's like that. All right. What we have to do now is to integrate, which is quite simple to do. So r equals rho over 2 pi L, and then 1 over r dr. Okay, 1 over r dr. And then we can integrate between a and b. That is the limits of r, and you will get a natural log function, rho over 2 pi L, natural log of b over a. You recall when we studied the electric capacitance of a cylindrical capacitor, we learned a special case, and that is when a and b are very close to each other. Okay, of course at that time there was vacuum a and b, but when a and b are very close to each other, then for any point in between a and b, each cylinder looks very much like very large flat surface, therefore should go back to the case of a parallel plate capacitor, right? Now in our case, what if a and b are almost equal to each other? Okay, if they're almost equal to each other, then this inner surface and this outer surface, they have almost the same cross-sectional area. So we can view this as a uniform cross-sectional area, and don't have to really integrate. Okay, we will recover the same, the similar result, which is just rho times rho times length, which is b minus a, divided by what? By the cross-sectional area. Whether it's pi a squared or pi b squared, who cares, because they're almost equal to each other. Okay, is that true when a and b are very close to each other? We're supposed to get this, right? Is that true from this natural log? Well, let's do that. Okay, let's see what happens. Now, b minus a, we call it d. Okay, so therefore I can write this as rho over 2 pi L natural log of a plus d. b is a plus d, right? Over a, and that is rho of 2 pi L natural log of 1 plus d over a. Now remember, d is the thickness between here and there, which in our case is regarded to be very thin. In other words, is far less than a. Okay, so the quantity d over a is very close to 0. So we call this x. So it's natural log of 1 plus x, x being very close to 0, natural log of 1 plus x. When x is almost equal to 0, what do you get? Don't you just get x, right? So this is rho over 2 pi L okay, times just x, which is d over a, which is d over a. Okay, do we get the same result? Well, it is rho times d. D is just b minus a, and it's what do we have now? 2 pi LA. Okay, it's a little different from here because we made a mistake here. The cross-section area is not pi a squared. We're not talking about that cross-section area. We're talking about the cross-section area of the cylinder, right? Of the cylinder. So this is not pi a squared. I'm sorry. It should be 2 pi a, the circumference times L. That was what's supposed to be. You see, they're exactly equal to each other. Okay, so that is yet another example of a non-uniform cross-section. What we do is we find dr of a certain thin layer, and then we integrate to get the total value of r. Our third example is unique in the sense that the way we solve it, it has to do with the exploitation of symmetry of the problem. We have here a three-dimensional circuit, okay? A three-dimensional circuit, not two-dimensional. And it's shaped into a cube. The cube is hollow, okay? It's really just a skeleton, okay? And each leg, okay, each side is made of uniform material of resistance R. So each side is just a resistor R. Now, how does one find the equivalent resistance, okay, between points A and B, between these 2 points? Well, if you were to measure such resistance, what would you do? What would you do? You hook up to a battery, okay? Hook up to a battery like this. So this is positive, this is negative, and then you find the total current. Right? If this is V, the voltage across the battery terminals is V, and if the current you get is I, then R equivalent would be what? V over I, right? V over I. Okay, the question is, how does one find I in terms of V? Well, it could be a complicated problem, but if we realize the symmetry of the problem, then it can be much easier. You know, these are 2 diagonal points, okay? And every single one of them has the same exact resistance. So there is symmetry, and that is, once the current, here's the current I, when it flows to this point A, it has 3 ways to go. 1, 2, and 3. And these 3 ways, as you can see, are equivalent to each other. So how should the current split? By symmetry. They should split evenly 3 ways, right? So how much does this guy get? It's got I over 3. So these 2, right? Now, once you get I over 3, you will reach this point with current I over 3. Now you got 2 ways to go, one this way, one that way. And once again, they are symmetrical. Okay? And therefore, they're going to split again evenly. So this I over 3, what do you get here? That would be I over 6, right? Half of I over 3. And this guy also I over 6. Okay, now, look at what happens here. Look at what happens here. The current here is the sum of the current flowing from here and flowing from there. This is I over 6. How much is that? Well, that current came from here, right? Came from here, which was split 2 ways. And this is I over 3, as you know, just like that. So I over 3 splits 2 ways. This is I over 6. This is also I over 6. So you got I over 6 going this way, I over 6 going that way. They recombine to form what? I over 3. Okay, now, suppose I follow a certain path, let's say this particular path, leading from A to B. Okay? What is the voltage drop between here and there? By Ohm's law, it is equal to I over 3 times R, right? V equals IR. I is I over 3 from between here and there. And then what is the voltage drop between here and there? That would be I over 6 times R. And finally, what is the voltage drop between here and there? That is again I over 3 times R. Now, voltage drop, voltage drop, voltage drop. If you add all the 3 voltage drops, don't you get the total voltage drop between A and B, which is V? Right? Okay? You add them all together, you get V. From that, we can find what R equivalent is. All I have to do is take V over I. There's I here. So V over I equals R over 3 plus R over 6 plus another R over 3. And that, as you can see, is 5 over 6 times R. That is R equivalent. We get that by simple analysis of symmetry.